Hey, oceanography students. So we've been talking about plate tectonics and we learned a little bit about what the major plate boundaries are and basically what plate tectonics is. So plate tectonics is also responsible for the creation of seas and oceans, volcanoes, islands, and mountains. And so we are going to talk about that today or in this lecture by looking at our plate boundaries in a little more detail to really see what's going on there. And in doing so, we will be able to understand how seas and oceans are formed and how volcanoes are formed and how islands and mountains are formed. Okay, so this plate tectonic map is figure 3.15 in your textbook. We're going to start out by going more in depth into the three types of plate boundaries. So I want you to take a minute to find a location on this map that is currently a divergent zone. And kind of recognize what type of crust is on each side of it. Okay, now that you've done that, if you haven't, pause the video. Now that you've done that, find one that is a convergent zone. And what type of crust is on each side of it? There are actually three different types of convergent zones based on what type of crust lies on each side. So you may have found a convergent zone that had ocean on both sides, or you may have found a convergent zone that had an ocean on one side and a continent on the other, or you may have even found one that had continent on both sides. Okay, so those are basically the three types of convergent zones, and we'll talk about that today. Or when I say convergent zone, it also, zone or boundary is the same thing, so don't get confused by that. So finally, I want you to find a transform fault zone. And you probably will find the one that we've talked about previously, but there are actually lots of transform faults if you look along the divergent zones. So notice that the divergent zones are not straight lines. Where the lines are kind of offset, you're going to end up with a transform fault in between them. Okay, so if you had found the convergent zones and divergent zones and such, you would have basically, these little jagged lines represent a divergent zone. So here's another divergent zone over here. And divergent zones, for the most part, are going to have ocean on each side of them, whereas convergent zones are going to be this little pattern down here, this little line with the triangles on it. So we've got convergent zones up here. We've got ocean on each side of those, right? You've got a convergent zone over here that's got an ocean on one side, a continent on the other. And then you've also got a convergent zone over here that's got actually continent on both sides, okay? For transform faults, this one is the most obvious, the San Andreas fault, which we talked about. But again, if you look over here along the offsets of the divergent zones, that right there where the cursor is pointing, that is also a transform fault right in between there. And we're going to talk a little bit more about that in the next video for you guys to get a better idea of how that could be. Okay, so first we're going to start out talking about divergent boundaries or divergent zones. So again, just to remind you, a divergent zone is an area where you have two plates that are moving away from each other. And the reason why the plates are moving away is because new crust is being created by basically molten rock rising up and hardening when it comes up here. And since there's new rock, it pushes the old rock away. So that's how we have a divergent boundary. I should say before this became divergent, these two plates would have been just one plate. The fact that they are two separate plates now is because of the heat that rose up and separated them. Okay, so divergent boundaries are really important for our class because they are what create ocean basins. All right, and this is showing you ocean basin creation in essentially 4 steps. Okay, or I guess it would be 3 steps. Okay, so step number 1, you've got a plate of continental crust here, and underneath it, of course, is the asthenosphere. Remember that the asthenosphere is going to be hot, And in some locations along our planet, that heat rises up and pushes on the crust above it. Okay, so what we end up with is sort of like this upwarping that happens, and over time, it basically causes the crust above it to actually crack. And so what ends up being created is actually what's called a rift valley. Okay, so the very earliest stage is actually just uplift or upwarping. Okay, and over time, as that crust has now cracked, now you can actually have new crust that's forming down here, and we can actually get the divergent kind of motion. Okay, so here is a visual depiction of what's going on. So we've got that heat coming up, creating new rock and causing the old rock to spread. Okay, now divergence and the first stage of ocean basin formation, what we have right now, we actually have on our planet on the continent, but there's no reason why it couldn't happen in an ocean as well. All right, so these pictures are showing you what happens if it's coming up to continental crust, but it could happen where there's already an older oceanic crust as well. All right, so the first stage, what we see currently on our planet, an example of the earliest stage of ocean basin formation is seen in East Africa. Okay, so if we zoom in right here, so here's Africa, here's the Red Sea, here's the Mediterranean over here, here's the Indian Ocean over here. All right, so if we zoom into this area right here, we are starting to see the newest stage of ocean basin formation. So what this area is called is the East Africa Rift Valley. And this is what it looks like. You can see that it is a valley that is being created because you've got crust that's getting kind of, it's going to be in the stage of getting pushed away, but it's not quite there yet. The second stage of ocean basin formation now, so now we're here, we have our Rift Valley. Over time, with more and more molten rock coming up, it's going to start hardening and forming new rock. And when it does, the continental crust, as far as this image goes, it's continental crust, is going to be pushed away. Okay, so this is the true divergence now that we are like really starting to have more new crust that's formed. And that crust that's forming is oceanic crust. Okay, so what we end up with when kind of an earlier stage, but after finding a rift valley, is a linear sea, because now we've gotten this land, this continental crust, to move away enough that now we have a big depression that ends up getting filled in, usually because it's connected to an ocean, and so ocean water will kind of come in and fill in. What this early stage of an ocean is called is a linear sea. And the reason why it's called a linear sea is because it is linear in nature. It's usually really long and thin. So it has a narrow kind of image or depiction to it. And on each side, you can actually match up the shoreline. All right. So a linear sea does not have all of the features of a mature ocean. So when we were talking about the different parts of or different provinces in a mature ocean in a previous lecture, remember we talked about trenches and we talked about mid-ocean ridges and abyssal plains. A linear sea is not going to have that. Okay, a linear sea is basically going to be just a depression, and it's going to have coastlines that match up. So it doesn't have a defined continental shelf or slope or anything like that. All right, and an example of that on our planet currently is the Red Sea. So as you can see, the Red Sea is a linear, very linear sea. It's narrow and long, and if we looked at each side of it, we could pretty easily see that the sides match up very well. Okay, and the reason why the tectonic activity that's going on that's creating the Red Sea is a divergent boundary, as you can see in this line right here. Okay, Now, as we continue to have more and more molten rock coming up and hardening, we end up with our final stage of ocean basin formation, where we get what's called a mature ocean. Okay, so finally, as the molten rock continues to rise up, it hardens, it creates new crust and pushes the old crust away, and we now have all of the features of a mature ocean. We will have a continental shelf, we will have abyssal plains, we will have a mid-ocean ridge, and a continental shelf on the other side. So now, in comparison to the linear sea, a mature ocean, when you look at the coastline, it's not going to match up perfectly. What actually matches up perfectly is the shelf break. Okay, so here's the continental shelf on this side. This is the shelf break. Here's the continental shelf on this side. This is the shelf break. And so we don't see that above water because it's under the water. All right. So I have a quick question. Does a mature ocean have a trench? You should say no. A mature ocean does not have a trench, because if there is a trench, that means that there's convergence going on in that ocean, and that means that the size of that ocean is shrinking, not growing. Okay, so if it has a trench in it, then it's either a declining ocean or a terminal sea, not a mature ocean. And you'll learn more about that in our next lecture video when we talk about the Wilson cycle, which basically describes the creation and destruction of oceans. All right, so an example of a mature or a fully developed ocean basin is the Atlantic Ocean, as we've previously discussed. Okay, so again, this is the Atlantic Ocean, and we can see that mid-ocean ridge going up the center there. All right, so divergence creates seafloor spreading. All right, so in places that are mature oceans or even declining oceans can still have a divergent zone in them. We have what's called seafloor spreading. It's basically another way for to say divergence, because divergence is basically created by new rocks coming up and then pushing the old rocks away. In other words, the seafloor is spreading away from that spot. So seafloor spreading produces 20 cubic kilometers of new ocean crust each year. So we have already talked about a ridge in the mid-Atlantic Ocean, but we can also call divergent boundaries rises instead of ridges. It just depends on how fast it's spreading, because the spreading rate will affect whether or not rocks pile up really high. A ridge is something that has like an underwater mountain chain, whereas a rise does not have the ability to have that mountain chain, that really defined structure of a mountain. So this image here, so here's South America, North America, here's the Pacific Ocean, and this is called the East Pacific Rise. And the reason why it's called a rise rather than a ridge is because it's spreading very fast, 16.5 centimeters per year. And that means that you can't really have a really defined pile of rocks to make a ridge. So instead we have what's called a rise. It just kind of slightly rises up. In comparison, the Mid-Atlantic Ridge, which we've talked about already, spreads at 2.5 centimeters per year. So it's spreading very slowly, and that gives it a chance to allow for the rocks to really pile up really high. Okay, so it stands up to 3,000 meters above the surrounding seafloor, with a rift valley up to 32 kilometers wide and 2 kilometers deep. Okay, so this is like a huge underwater mountain chain, essentially. And the way that I like to describe it is that if you, whoops, it's taking a while. If you have some rocks and you just like pile them, just drop them, they're not going to really pile up, okay? But if you very slowly place those rocks on top of each other, you can make your pile of rocks grow pretty tall. So that's basically the same thing. This pile over here, this pile of rocks, is going to be like a ridge where it's spreading slowly enough that the pile can really pile up, whereas this animation is going to be similar to a rise, where it's coming up so fast that the rocks just kind of fall over. So instead of having a big mountain ridge or a big mountain chain, you end up just having kind of a elevated area. All right, now the next type of boundary is called a convergent boundary, which we learned about in the previous video. So this is where you have two plates colliding or coming into each other. And there are three different types of convergent boundaries based on what type of plate is on each side of it. So you have ocean-continent convergence, where you have ocean crust on one side of the plate boundary and continental crust on the other side. And when those two things collide, the oceanic crust is then destroyed, which we'll talk about in more detail in a minute. The second type is ocean-ocean convergence, and this would be basically where you have ocean crust colliding with ocean crust. And in this case, usually one set of ocean crust is going to be older than the other one is, and that makes it denser. And therefore, it's going to go underneath the newer crust and get destroyed by going into the asthenosphere. The third type is the continent-continent convergence, and this is where you have continental crust colliding with continental crust. In this case, they basically just pile up instead of either one being destroyed in the mantle. Okay, so looking at this map again, we are going to look for a location that has ocean-continent convergence. And you can find a couple of them, but a really obvious one is down here between the Nazca Plate and the South American Plate. Okay, so you can see ocean crust on one side and continental crust on the other side. Okay, another location is up here along Washington, and another would be right down here on Central America. So let's see what's going on here and what kind of features end up getting created. Okay, so again, one type of convergence occurs between oceanic crust and continental crust. So in this image, here we have oceanic crust on this side, and here we have continental crust over on this side. When these types of crust collide, the oceanic crust is subducted or pushed down below the continental crust. So if we look down here at the crust, we see continental crust, ocean crust. The ocean crust is going underneath the continental crust. So it's going back into the earth, into the upper mantle or the asthenosphere. So the reason why it's doing that is because the oceanic crust is denser than the continental crust. So the subducted oceanic crust moves into the hot asthenosphere or upper mantle where it melts because it's hot, okay? The melted material then seep up and rise up into the lithosphere where they then harden and create new crust. So basically the crust then piles up in those locations and you get mountains. So the mountains end up being volcanic because they're driven by molten rock, or which basically are volcanoes. So volcanic mountain chain is created because convergence is in a line rather than just being one little spot. So instead of just creating one little volcano, it creates a whole chain of volcanoes and a whole chain of volcanic mountains. Okay. Also, anywhere in which there's a convergence in the ocean, a trench is also created. So I wanted to highlight that for you. Okay, so off of the continent where you have ocean-continent convergence, you're going to have a trench. So as you move off of the continent, off the shore, you're going to have a really steep drop-off all of a sudden in places where you have ocean-continent convergence. And we would actually call that an active continental margin rather than a passive continental margin. No, passive would be someplace where there's not a trench and there ends up being a really wide continental shelf, whereas when active, you have a really narrow continental shelf because you have a sudden drop-off. Okay, so what we've described with the ocean-continental convergence is representative of what's happening in South America. So over here would be the Nazca Plate, and over here would be the South American Plate. and they are colliding and they're creating the Andes Mountains. Okay, and note that I'm really trying to make sure that when I say the mountain chain, I'm emphasizing that it is a volcanic mountain chain, because there are also mountain chains that are not volcanic because they're created by different processes. And we'll talk about some of these processes today, actually, in this lecture. Okay, so we just went over ocean continent. Oceanic plate is destroyed. You have volcanic mountains that are created in this example. And now we're going to go on and talk about ocean-ocean convergence, in which the denser oceanic crust is destroyed and what kind of features we end up with in that case. Okay, so now let's find a location or two where we see an area with two oceanic plates that are converging or colliding. So what we're looking for is a spot that has the little red triangles. See these little red triangles down here? Has little red triangles, and it's going to have ocean on each side of it. And you should see quite a few, actually. So this one here is showing you convergence between the Pacific plate and the North American plate. This one here shows you convergence between the Pacific plate and the Eurasian plate. This one is showing you conversion between the Pacific plate and the Philippine plate. And then this one down here is showing you convergence between the Pacific plate and the Australian plate. So there are plenty more you could also identify, such as over here in the Caribbean, over here on this other side of where we circled before. So there's lots of examples of this that we see on our planet today. All right, so let's go ahead and look at what's actually happening at each of these locations, these ocean-ocean convergence zones. Right, so this image should look similar to the previous image, because the process that occurs at ocean-ocean convergence zones is very similar to what occurs at ocean-continental convergence zones. They both have oceanic crust subducting into the asthenosphere or upper mantle, and crust melting and rising up to the lithosphere. The difference is that in ocean-ocean convergence, the lithosphere is made up of oceanic crust rather than continental crust. So instead of getting volcanic mountain chains, as you would with ocean-continental convergence, you get volcanic islands. Okay, so we've got ocean crust on this side. We've got ocean crust over here, and they are two separate plates. Okay, so essentially, probably ocean crust that got created at different times. They're meeting up, and apparently the ocean crust over here on the left side is older than the oceanic crust on this side. So it ends up, because it's denser, going down below the newer oceanic crust. And when it does, it goes into the asthenosphere, it heats up, it melts, and it rises up as molten rock. It hits the oceanic crust above it, and it cools and builds new rock, and it builds and builds and builds and builds and builds until eventually you have an island peeking out above the surface of the ocean. Okay, now this is not just happening at one location, it's actually happening in a line all along where this ocean plate is subducting down below this ocean plate. So instead of just having one island, we have a whole row of islands, which we refer to as an island arc. Okay, and we refer to this as an island arc instead of an island chain because we are distinguishing it as it being created by ocean-ocean convergence. Okay, and as I pointed out to you previously, when you have convergence in an ocean, you will always have a trench. So when you've got an island arc, alongside that island arc in the same, right alongside it in the same kind of pattern, you're going to have a trench. Okay, you're going to have a trench basically lining the island arc. All right, so let's look at the ocean-ocean convergence that we highlighted previously and see what kind of features exist there. Okay, so as we just learned, ocean-ocean convergence creates volcanic islands. Okay, so let's see, the first one up here, we have a convergent zone between two oceans, which is one ocean is on the Pacific plate, the other one is on the North American plate, and what we have created here are the Aleutian Islands. So again, you have an island arc there. Over here, we have the islands of Japan. Down here, we have the Marianas Islands, and of course, more famously, the Marianas Trench. Okay, so like right here, you've got the Marianas Islands. So what that should tell you is that the Pacific plate is subducting below the Philippine plate. All right, and that's why they're popping up over on this side. All right, and then down here, we've got islands like, there's actually lots of islands around here. We've got islands like Fiji and New Zealand as well. All right, so finally, let's get to the last type of convergent boundary, the continent-continent convergent boundary. And in comparison to the other two, this is very different because neither plate, when two continents collide, neither type of crust is destroyed. Okay, so now we're going to finally find a place that shows continent-continent convergence, and I've already highlighted it for you because there are not as many. The best one, this is kind of the best example of it. So at this location, you've got the Indian plate down here colliding with the Eurasian plate, all right? And so that is showing you that's the convergence zone. That's where they're actually meeting up. So let's look at what's going on here, right? So in this image, again, we've got continental crust over here, we've got continental crust over here, and they are separate plates, but they are mashing into one another, okay? So this type of convergence is only similar to the other two in that it exists where two plates are colliding. It's very different because one crust does not subduct into the asthenosphere. So the continental crust from one plate pushes on the continental crust from another plate, and that results in a mountain range that's not volcanic. So as you can see, when we look, it looks like one is kind of going down below, but it's not going all the way into the asthenosphere where it melts. Okay, instead, what's happening is you can see you've got lithosphere hitting lithosphere, which results in basically folding up, or a mountain range that's not volcanic. And you could actually see this motion yourself if you just took a piece of paper and put it on a flat surface, like put it on a table. If you take your hands, put one hand on the right side of the paper and one hand on the left side and push it together, you should see the paper fold up. And that's the same kind of motion that is creating these mountain ranges. So you may recall from your mapping exercise what famous mountain range is located over here. It is the Himalayas. So you can see here's India down here, here's Asia, the rest of Asia up here, and you've got the Himalayan mountains right along it. All right. So here summarizes the three different types of continental plate boundaries. You've got the ocean and continental plate boundary that creates volcanic mountains. You've got the ocean-ocean convergent boundary, which creates a volcanic island, or specifically called an island arc, because there are other volcanic islands as well, as you'll learn in the next lecture video. And then down here, we've got the continent-continent convergence, which creates non-volcanic mountains. Okay, now let's talk about the third type of plate boundary, which is the transform fault boundaries, in a little bit more detail. There's not as much detail as the other ones, but because this is kind of like a side to divergent boundaries a little bit, but they still are important. They still cause lots of stuff to happen, okay? So if we look over here on this map, we can see lots of different examples of transform fault boundaries. The one we've talked about previously was the San Andreas Fault, which is right here, all right? So the San Andreas Fault, you've got this plate moving up to the north, and that again is the Pacific plate, and you've got this plate, which is called the North American plate, moving down towards the south. But if we look up here, this purple represents a ridge called the Juan de Fuca Ridge. So this is an area of spreading that started a long time ago, and it's basically kind of getting pushed out so that it's not really spreading a whole lot anymore. But we can see along the sides of it that it's not a straight line. So because it's not a straight line, because it's offset over here, we've got the spreading center here, and then as you go farther down, you've got the spreading center all the way over here. On each side of the spreading center, the divergent boundary, you've got a different plate. So you've got this plate moving to this way, you've got this plate on the side moving this way, that's why it's divergence. But down here, you've got also divergence, but notice that the plates on either side of this little line are going in different directions. So this plate is moving towards the southeast, and this plate is moving towards the northwest. What creates in between that is, again, a transform fault boundary. When you move farther out, you don't have a transform fault anymore because you've got stuff on the same side moving together. And what we call those are fracture zones. So again, if we zoom in to this kind of little section right here, we see this is the divergent boundary and it's offset over here. So this is the divergent boundary right here. So if we move this way here, but down here we're moving in the opposite direction, we create a transform fault in between the offset of the ridges. Okay. Now outside, beyond the offset, you also have kind of a fracture, and that fracture is said to be inactive. The reason why it's inactive is because if you look at the south side of it, you've got a plate that's moving towards the right. If you look at, or the east, and if you look at the north side of it, you also have a plate that's moving towards the right or the east. So it's the same plate on either side of a fracture zone, and therefore there's no motion there to create any kind of fault. But if you've got in between the divergent boundaries, you've got two different plates. This one is moving towards the east. This one down here is moving towards the west, and therefore in between that boundary between them would be considered a transform fault. So another way that mountains can form is by way of transform faults, because it's essentially compressing rock. And one example of this occurring really close to us is Mount Diablo. It rises to about 3,849 feet tall, and it actually is continuing to rise at a rate of about 2 millimeters per year because the fault is a fault. It's active. So it's essentially like compressing the rocks and causing them to rise up. All right, so you've got, and this is also non-volcanic, because you don't have any heat coming up. Instead, it's just created by two plates sliding past each other and squeezing the lithosphere in between it.
Okay, so if you have any questions, please let me know. In your weekly discussion, I want you to also include the following answers to the following questions. What geological features exist around a continent-continent convergent boundary? What features exist around an ocean-continent convergent boundary? And what features exist around an ocean-ocean convergent boundary? Okay, and there is another video after this one, so make sure you continue and watch that too.